Thank you for joining us today for this talk about application modernization, specifically about database modernization. We've seen lots of innovation in other parts of the application stack, lots of innovation in front ends, in our middle tier business logic, innovation how teams are structured, how they push code through the development lifecycle. But we really haven't seen the same pace of innovation at the database layer. While there's certainly lots of different kinds of databases, and we'll talk about a few of those today, relational databases are still the workhorse for many applications in financial services. So what we're going to talk through today is how we can apply some of those modernization techniques to the database tier. My name is Kenneth Jackson. I'm a Principal Solutions Architect in the Global Financial Services Group here at AWS, and I'll be joined in a minute by my colleague Andrew Short, who's also a Solutions Architect in GFS. So what do we want to cover today? We first want to make sure that we enumerate the requirements that financial services firms have for the database tier of their applications. Financial services firms have stringent demands for performance and availability and security for this database tier. And we'll talk about what are some of those requirements, but then we'll try to be honest about some of the pain points where meeting those requirements with traditional relational databases exist, where that causes unnecessary cost or complexity or both. And we'll talk a bit about some of the innovation we've done on database engines here at AWS with a focus on two, Amazon Aurora and Amazon DynamoDB. But then we'll try to get very practical at the end with some tips on how you can modernize the database tier of your applications. And then we maybe point you, we only have half an hour or so to talk about this today, but we want to point you towards some other resources where they go in much more depth and detail about how you can execute on our advice today. So let's just remind ourselves what kind of demands financial services firms place on their database engine. First, for any system that is significant, we need performance, right? Think about online banking systems or payment systems or trade reconciliation systems or many others. We need performance that gets easily into the thousands or tens of thousands of transactions per second. But we have a broad community. We may have tens of thousands of engineers building applications in our firms. We need technologies that are easy to use and apply. We need a way of interacting with them, of getting data in and out and transforming data that applies not just to professional developers, but to semi-professional developers and administrators as well. Many of our systems are dependent on transactional integrity. That's really one of the features of relational databases that have led to their popularity, right? We want a credit and a debit to exist on either both sides of the ledger or neither side of the ledger, right? And transaction monitors, ACID compliance, distributed two-phase commit, these stalwarts of relational database technology are one of the ways we've ensured that transactional integrity. But as the world has gotten more complex and we've added support for web applications and mobile applications, both interactive and batch, or applications that have to run 24/7, 365, as modern programming languages have gained in popularity, we need our database engine to be flexible as well. And finally, both to meet obligations to our customers and to our external regulators, we need data that's guaranteed to be durable, right? We can't lose data. We're required to retain it. Again, we don't want to lose a transactional history to be able to test that what we did was the right thing for a customer or to recover in the case of a disaster. So we need our database engine to be durable. Relational databases both execute on all these things, but also come with some drawbacks, right? If you go and look at the latest TPCC benchmarks, you'll see that it's possible to build relational database layers that scale to hundreds of thousands of transactions per second. But if you drill into the hardware and software stack, you'll see that it's quite complex and relatively expensive and fragile. And SQL is also very popular. It's easy to use, easy for a non-professional developer to pick up, but it the trade-off is it lacks a lot of the conventions that a modern language would support. As one example, think, where are the package libraries that are maintained for SQL, right? That tends to be sort of cut and paste reuse. It really doesn't have a mechanism built in to extend my code with someone else's code that's been tried and tested and vetted for performance and accuracy. It's really on me to do most of that code writing. So the flexibility comes at a cost in terms of extensibility and stability. Relational databases are great at enforcing consistency, as I already said, through ACID compliant transactions and through these transaction processing monitors that can scale up. But again, that adds complexity and cost to the software stack, right? It also adds fragility. I've taken a single point of failure. If that thing isn't working, then my whole system isn't able to respond to customer demands. Where relational databases have really shined, maybe in the last 10 to 15 years, is their amazing flexibility. You can now write store procedures not in a SQL-based language that's native to the database, but perhaps in a modern language like Java or one of the .NET languages. You can build all kinds of systems out of relational databases. For example, consider maybe an anti-money laundering and anti-fraud system at a bank. Fundamentally, these systems are looking for relationships between entities, and you can certainly do that by complex queries that code rules into SQL statements looking for the relationship between this entity and that entity with some sort of join. But those get very complex, right? Where maybe a database built for relationships, something like a graph database, would be much better suited. And relational databases do deliver amazing durability, right? You can get your recovery point objective to 0 or very near 0, but it usually requires combining your relational database engine with modern storage and then proprietary software on top of that modern storage to guarantee that durability. So I guess the takeaway from this section is we've done amazing things with relational databases in the 40 years since they have been commercialized. We've made them fit interactive and batch workloads, analytics workloads, transaction processing workloads. We've added support for a variety of languages and data types, and we've met the most stringent requirements for financial services applications. But that's come at a cost, and that cost is in terms of real cost of maintaining the system, but just the opportunity cost of the labor and the effort it takes to get these properties out of the databases. And that means we can't use that talent to do other things.
Great. Thanks a lot, Ken. So we're going to be talking about a couple AWS database innovations that we've built over the years, and we've tried to fundamentally rethink the way that databases are designed and built from the infrastructure layer up, and taken a modern twist on a lot of the same use cases that the financial services industry has been supporting for a long time. The first of those databases is Amazon Aurora. So Amazon Aurora is our enterprise relational database, but using open source pricing and open source technologies. We've fundamentally rethought the way that relational databases are built. We have a separate storage and compute layer that automatically spans various different availability zones, so you get high availability out of the box. You can scale up and scale down the compute instances as the nature of your workloads change. You get the speed and availability of the high-end commercial databases, but at those open source prices that are so important to our customers. As financial services customers yourselves, you probably know that speed and availability are not two things that you can trade off when looking at a database, as you're often supporting real-time systems, trading systems, or sources of record that absolutely have to be available all the time. And Aurora doesn't make any trade-offs in those areas. And additionally to those things, Aurora offers the simple pay-as-you-go pricing that you've come accustomed to running other systems in the cloud. So you no longer have to over-provision your database infrastructure in order to handle the peaks in demand that it might see during the day or throughout the year. And then best of all, it's got drop-in compatibility with MySQL and PostgreSQL. So you're no longer locked in to a proprietary database language, and you can port your existing databases that you've built in those two languages to Amazon Aurora, or use all of the open source tooling that's available for MySQL or PostgreSQL in order to convert and utilize the Aurora benefits that we've created. Aurora has become very popular with many of our financial services customers, some of which we've presented in front of you today. Specifically, Intuit was able to use the Aurora Global Database in order to provide AWS multi-region availability and AWS high availability. So one of the key innovations with Amazon Aurora, like I said, is the Scaleout distributed architecture. So the first thing we did was we built a purpose-built log-structured distributed storage system designed specifically for this database. The storage volume is striped against hundreds of nodes across 3 availability zones, and then each piece of data is stored 6 times. So that means we can handle the full failure of any given availability zone plus another node and still be able to maintain the same availability and durability characteristics that we promise to our users. This is super important because previously with traditional database platforms, in order to get multi-data center, cross-data center availability, it was extremely complex to design and implement these types of technologies. And AWS has done that behind the scenes for you, so you no longer have to buy and procure expensive hardware and go through the pain of having to plumb those things together the right way in order to get your high availability goals achieved. Also, we write data into what are called protection groups. These are 10 gigabyte blocks that dynamically grow as your database scales. So you don't have to start off with a certain high provision amount of storage and then go through large storage refreshes as that database size increases. Aurora dynamically increases the space that you're provisioned as you need it, and there's no manual action that you have to take in order to achieve that benefit. Next, we're going to be talking about DynamoDB. So DynamoDB is Amazon's fast, flexible, and NoSQL database, really for any scale application. NoSQL databases really emerged over the last 10 years as great key value stores in order to store and retrieve fast, transactional, key lookup use cases that you need to be able to massively scale. And DynamoDB delivers that by horizontally spreading the data that it's storing across many different nodes in the AWS region and providing you single-digit millisecond latency or even microsecond latency when you use our DynamoDB accelerator, which is a memory cache for DynamoDB. It can scale up to millions of transactions per second, which satisfies the needs of the most demanding financial services applications. And we have automated global replication with DynamoDB global tables. In addition to all these features and benefits, there's no servers for you to manage, nothing for you to provision ahead of time. Will automatically scale up and down the provisioned capacity that you need if you want us to do so. Enterprises have come to expect ACID compliant transactions, particularly in financial services when you're coming from a relational database. DynamoDB offers strong consistency and eventual consistency on reads. And in addition to that, there is a ACID compliant transaction that you can use for multi-phase commits and other things like that in order to match the design needs of your applications, particularly ones that you're bringing over from legacy applications. It comes with encryption at rest, on-demand backup and restore, and then we offer a new client-side application called the NoSQL Workbench that you can use to model, view, and test your queries before you put them into production. This has also been an extremely popular database embraced by our customers.
Thanks, Andrew. Well, let's try to get practical now. How can you leverage this innovation at the database layer, which Andrew discussed, in engines like Aurora and DynamoDB? Our first tip is to take your scarce IT and engineering talent and reapply them to more valuable tasks. Tasks that are closer to the actual business logic, the actual differentiation in your applications that helps your firm compete, rather than commodity tasks like patching databases or upgrading the operating systems on which the databases run, or taking backups of the databases and ensuring that those backups were stored, and managing the storage that's attached to these databases, right? If with a system like Amazon Aurora, all of that is part of the service, part of that pay-as-you-go offering, which Andrew discussed. Right? You do have maintenance windows. You have some control over when you move from one version of the MySQL or the Postgres engine to another, but that actual work and doing the migration in a way that's low risk to your application is the responsibility of AWS as we operate the Aurora service. You don't worry about server provisioning. You don't worry about the underlying operating system or networking or storage that is required to run those database engines. You also get dynamic scaling, which is not only really hard when you're doing this on-premise, but it also has little value. Let's say you were to scale back your production relational database during off-peak times, or let's say you were to scale back or turn off your lower-level environments like development and UAT when they weren't in use. The risk of doing that, the risk of things not scaling back out or coming back on and disrupting your customers or your development teams, far outweighs the value you might get by turning those off, because that server capacity, that storage capacity, those software licenses aren't fungible. But with an engine like Aurora or DynamoDB, which is pay-as-you-go, you can scale those things up and down. Just consider Aurora for a moment. It has primary nodes that are receiving your queries, and then it has replicas for either analytics but also for high availability. But consider a time where either you had where production load was decreasing, or you had a development environment that could scale down in off hours. You could scale down, take a secondary node out of service, scale it down to a smaller instance size, cut over to that node as the primary, and then scale down the secondary node, or even turn off some of the secondary nodes when your analytics workloads weren't running. Right? Again, that's something that would be very hard to replicate on-premise, but it's just part of the service and would free up those resources for innovation in your actual application. Additionally, your staff will be no longer responsible for maintaining the availability of these relational databases. Today, you have to size for peak. You have to have not only the capacity in your primary region to satisfy your customers under the biggest demand, but you generally have to replicate that in another data center, and it mostly sits idle. The way that Aurora and DynamoDB are architected on top of the Amazon regions and availability zones mean you get that availability without doing any additional work. You can survive power and networking failures without having to go to asynchronous replication models. You can design the system as if it's one system, but it still has the availability properties as if it is a geographically distributed system. And that failover is automatic. When Aurora detects a failure in one node or detects a failure in one availability zone, it will automatically start shedding traffic to the other one, so you get those availability properties. Our second tip is, so if the first one was really about freeing up your database administrators and your infrastructure engineers to focus on more high-value tasks, our second tip is about making your developers much more productive and allowing them to choose the best database for the job. As I mentioned earlier, relational databases were commercialized in the early 80s and became very popular, both commercial and open source databases. And they tended to be the tool that we applied to every job where data was required. As I mentioned earlier, consider a scenario where my data is highly integrated, right? Where I'm trying to figure out what are all the relationships between one transaction and another, so I can detect and score whether it is fraudulent or not. You certainly can do that with relational databases. And if you're a longtime relational database programmer watching this, you're probably thinking of, oh, how would I solve that, right? I'm going to have to join this table with that table. I'm going to have to, maybe do some string matching to see how similar one thing is to another. But also, if you're an experienced relational database programmer, you're starting to think, oh, how complex is going to be, and how am I going to make that performant? What types of indices do I have to use? And what you're really saying is maybe this is not the right tool for the job. Maybe I need a tool like a graph database, like Amazon Neptune, that understands relationships and is optimized for querying those relationships at a deep level. And that's just one example. All right, the AWS family of database engines is meant to cover all of those use cases and let you pick the one that's right for the job. The example we have here on the slide, again, think about a typical transactional web application, right? I first need to authenticate my users and authorize their access to the system. I then need to keep up with state as they're progressing through the application, so that if they go forwards or back, I remember where they were and I can render the information correctly. But then I have the actual point of the application. I have transactions. Maybe this is an online banking type application, and there are lots of bill pay entries or credits and debits. And then in the back end, I need to do some reporting off of that. Well, today we might solve all of those with the same relational database technology. But you think about the very read-heavy authentication and authorization that happened at the front, right? Well, now I'm going to run that through a transactional processing system, right? And that's going to be much more expensive. It's not going to scale as well. I'm going to scale that up vertically. Same can be said for the session data, right? Again, that's mostly read, some writes, but I'm going to be querying that a lot to make my system scale out. But the transactional part of the system, where I actually want those credits and debits to reconcile and either all succeed or all fail, that may still be a great case for a relational database like Aurora. On the analytics side, that could be, if it's relational and traditional SQL queries, that could be Aurora, or it could be something like a multi-dimensional column or data store like Amazon Redshift. The point being is, if you were to try to implement this pattern with the traditional ways that you build systems and just let developers choose the database they want, you have the costs of acquiring and maintaining lots of those technologies that would make it impractical, which is why we've tended to stick with one or two relational database engines and just solve all these problems with that. AWS makes that possible to because you pay as you go, because you don't have to worry about all those maintenance tasks, that you can allow developers to choose the best technology for each part of the application.
Great, thanks a lot, Ken. So our modernization tip number 3 is all about harnessing the power of the API. So this is less about the specific database that you choose and more about how your users access that database and how you share that database with other teams in your organization. Traditionally, if other teams needed to use the data that your system was processing, they would make JDBC, ODBC, open database connections into your data store and then query that data to get what they needed. Over time, you could have dozens or even hundreds of applications that may not even be owned by your team connecting to this data store and running queries. There's a lot of different problems that come up when you do that. As you've probably experienced, first of all, when you go to make schema up changes or upgrades to the database version, you can adversely impact applications that you weren't even aware of how they were querying your database. By tightly coupling the schema to these other consuming applications, you've now created a huge dependency on doing upgrades and achieving the velocity you want as an application team and as a team who's trying to meaningfully upgrade the database in order to meet your user demands. So if we're taking this modern look at databases, we've started to have databases that are with automated management. We have teams owning their databases and using the database that's right for the job. The next step is to really put in front of your databases modern communication tools and contracts for other teams to be able to consume that data. And oftentimes in today's microservice world, that's an API. The great part about an API is it's a well-formed interface with other teams. It abstracts away the details of your schema. So your team is free to change out the database type or to change the schema without the consumers of your application ever even knowing. This gives you a lot more freedom when it comes to achieving development speed and choosing the right database, and then also separating your application behind the scenes in order to use either multiple data stores or dividing it into multiple services from one service. There's a bunch of other benefits that this can provide as well. First of all, from a security perspective, you can enforce proper TLS enforcement, modern authentication patterns, such as in Amazon. When you're connecting to Amazon Aurora or DynamoDB, you can use our IAM authentication protocol instead of using something like a standard database string, where you're going to have applications connecting over the wire with their username and passwords, and they're going to have to figure out some way to store securely those user and passwords and then rotate those credentials. When you use AWS IAM, that's already managed for you. Connection pooling for database systems can be a very resource-intensive process, and it can also often be a huge failure point for applications that are connecting to a database, especially when you've shared out those database connections to other teams that you can't control how they're going to use it. So by enforcing an API as the interface into your database system, you are essentially pulling connections at a central point where you can do throttling, you can do verification of the data that they're requesting. So SQL injection security risks are all of a sudden reduced significantly. And you can significantly reduce the computational load on your database of having to manage dozens or even hundreds of connections from disparate applications. That's now being handled by your application, and you're using a proper connection interface like an API in order to manage that for you. This is the pattern that Amazon.com started using many years ago, and one of the reasons that we've been so successful and able to achieve speed and pace of innovation. So with that, Ken and I are going to close out. We'd like to point you to a couple additional resources that you can look up after this talk and dive deeper into the topics we're talking about today. The first is a talk that Vanguard did at AWS reInvent about how they transformed from monolithic mainframe-based applications into DynamoDB principally, and how they broke apart those monoliths into microservices.
Yeah, and the second one, as Andrew was just alluding to, is the story of our own journey. It's been well publicized, the move from traditional commercial databases to our own Aurora database, and there's a lot of devil in those details, and this talk goes into some of those details. And again, if you're a relational database programmer or DBA, you may be thinking, yeah, what about differences in SQL syntax? What do I do about stored procedures? What do I do about, how do I do a cutover? Yeah, this talk goes into lots of detail on how we did that at scale for thousands of commercial databases here at Amazon. And then the others will just commend to you as other ways to get you thinking about how you can take advantage of modern software development practices at the database layer. Again, that's that last frontier for modernizing how we build, maintain, and evolve applications in financial services. So thank you so much for taking the time to watch. If you have any feedback, please do leave that. There's a mechanism to do that here on the screen. And again, thanks